In this demo, we are using ATECC command line interface. The ATECC command line is a unified tool to manage your ATECC service. We need to have ATECC command line installed and log in. The first step is to set up a sophisticated chain of trust that resembles a production IoT ecosystem. For the testing purpose, we will create a self-signed root certificate authority, RISC-V, and an intermediate certificate authority. Your RISC-V will be self-signed at the top of your chain of trust. Your signing certificate is an intermediate CA and will be issued by your RISC-V. It will be used to issue to your device certificate. Your device certificate will be a unit per device and is issued by your signed certificate. Step 1. Create RISC-V. First, create your RISC-V. The RISC-V will be the trust anchor from which the whole chain of trust is derived. Microchip has created a tool to create a RISC-V using Python. We will use this tool to create our RISC-V. Step 2. Create a signing CA. The next, create your signing CA. The signing CA is an intermediate CA and is issued by the RISC-V. It will be used to issue your device certificate. The purpose of creating and using intermediate CA is primarily for security, because if the intermediate private key is compromised, then the RISC-V can revoke the immediate certificate and create a new one with a new cryptographic key pair. This CA certificate will be registered with your ATECC IoT account. Step 3. Run CA create sign-up PI script to generate the signing CA certificate and key. Microchip also create a tool to generate a signing CA. Run this script, we could generate the signing CA certificate and key, as well as the verification certificate. The signing CA certificate and key will be used to issue your device certificate. The signing CA certificate is an ATECC608 certificate that contains the public key and is signed by the RISC-V we just created. The verification certificate is used to register your signing CA certificate with ATECC IoT in the next step. Step 4. Register your CA certificate with ATECC IoT. Because we are using the self-signed RISC-V, so ATECC IoT doesn't recognize. Therefore, we need to register the CA certificate with ATECC IoT. Now, register your CA certificate with ATECC using ATECC command line. ATECC command line will send the signing CA certificate to ATECC to register that certificate with ATECC. It also sends the verification certificate with creatable to prove that you own the private key associated with the CA certificate. ATECC command line is using HTTPS to send data to ATECC, so data has been encrypted. The private key won't be sent to ATECC. Did API return the certificate ID for your new CA certificate? Certificate ID is the 64-character hash value. It is used to identify the certificate from older certificates registered on ATECC IoT. The ID won't be added to the device at 409 certificate. Step 6. Your signing CA certificate is now inactive, meaning that it cannot yet be used. Activate now. By default, the certificate is in inactive state. When we register it with AWS, it means that the certificate is in AWS server already, but it cannot be used yet. We need to activate it. Step 7. You have now created your signing CA and register it with your AWS account. the CI certificate can be used to cite device certificate, which can be then registered with AWS IoT. Now we will create a device certificate. For each device that you want to register with AWS, you will need to generate a unique key and a corresponding certificate. First, ensure that a fresh key pair will be generated. We'll choose the FreeRoT code and open the demo project. Browse to Demo Dev Smart Key Provision Source. Deal with AWS Dev Smart Key Provision file. AWS Dev Smart Key Provisions is used to provision key and certificate for FreeRTOS. Without ATECC608A, the key space generated using software and is saved in flash memory, so it could be leased. When using ATECC608A, the key pair is generated in ATECC608A. The public key and device serial number can be exported from ATECC608A, but the private key will never leave the ATECC608A. ATECC608A use elliptic curve cryptography (ECC) as shown in its name. ECC has some advantages. A shorter key are as strong as long key for RSA, low on CPU consumption, low on memory usage. Step 11. Change macro key provision for generate the new key pair to 1. Changing this macro to 1 to force the device to generate new key pair each time it runs. The public key and device serial number can be exported from the ATECC608A. We need this information to create device certificate. Step 12. Build project. Build the FreeRTOS project. Step 13. Burn the firmware to MCU. Flash the firmware AWS demo.pin which is built to MCU. Step 14. Reset the MCU to put up the new firmware. The FreeRTOS will be booted up here. When the device boots, it will be generate private key. We never leave the ATECC608A. I will add a public key. The step 15. The public key and device serial number are imported from the ATECC608A and printed to the console. After the key pair is generated in ATECC608A, MCU will get the public key and device serial number from the ATECC608A and print them out. The serial number is 19 characters following CN. The public key is a 91 byte in hash format printed in SHITLINE. Step 16. Copy SHITLINE public key byte into a file called device public key ATECC608A. The file contains only the public key. 17 step. Currently, you can see the system cannot connect to AWS. The device using the newly created key pair to communicate with AWS, but AWS doesn't have any information about the new key pair yet, so the device could not establish the connection to AWS. Now we will create the device certificate with public key and device serial number, sign it with the sign-in CA we created before. The Python tool to create device certificate needs the public key in PEM format, so we need to convert the public key from hash number to PEM file. The easiest way to accomplish this is convert the public key from the hash number to DER format using ATECC tool, and then convert the public key from DER format to PEM format using OpenSSL tool. What are the DER and PEM formats? DER, distinguished encoding rule, the binary encoding for certificate data. PEM, privacy enhances electronic mail. The basis for encoding of DER encoded certificate with a header and footer like this. There are two main methods for encoding the certificate data. Step 18. Use the command line tool ATECC to convert the public key to DER formats. This step will generate the device public key der.ping file. It is the public key in a DER format. Step 19. Use OpenSSL to convert public key from DER format to PEM format. This step will generate the public key .pem file. It is public key in PEM format. Step 20. Change macro key provision 4 generates new key pair to 0. Don't forget to disable the temporary key generation setting. You enable both. Otherwise, the device will create another key pair and you will have to repeat the previous step. Step 21. Create the device certificate. Use the CA create device script. Use the 18-character serial number for the team name and the publish key.pem file that you format as your public key. You now have device certificate called device.crt. This certificate will be used to authenticate your device with AWS. Step 22. Register with AWS IoT. Now, when the device certificate has been created, let's set up your device with AWS IoT. Step 23. Register your device certificate with AWS IoT. This step let AWS know that your device certificate is linked to your account and that the signer CA you previously created is above your device certificate in the chain of trust. The output is the certificate ID of your device certificate. Take note of your certificate ID, and it will be used later in the instruction when we attach a policy to it. Step 24. Activate your certificate. The certificate is in inactive state by default when you register it. Now use AWS command line to activate it. Step 25. Create a policy called Demo policy for your team certificate. In AWS IoT policy, is a JSON document that indicates the accept right to AWS IoT service. AWS IoT policy is used to authorize your device to perform AWS IoT operations such as subscribing or publishing to MQTT topics. Your device presents its certificate when sending message to AWS IoT. To allow your device to perform AWS IoT operation, you must create an AWS IoT policy and attach it to your device certificate. For this demo, we will create a policy to allow our device to connect publish, subscribe, receive to AWS IoT. In this video, the policy has been created before, so we don't need to recreate. Step 26. Attach the policy to your device certificate. When we attach a policy to the certificate, we have set the accept right for the certificate. It means that the device we use the certificate will have the accept rights that defined it in the policy. Step 27. Create a theme. This is the digital representation of your device in AWS IoT. An IoT theme is a representation and record of your physical device in the AWS IoT cloud. Any physical device needs a theme record in order to work with AWS IoT. We will create a theme with a theme name is 18-character serial number obtained from the ATECC608A. Step 28. Attach your device certificate to your theme. Now associate the device certificate with the theme we have just created. The certificate is now ready to be used. Step 30. Get the endpoint of AWS IoT. To connect programmatically to an AWS service, you use an endpoint. An endpoint is the URL of the entry point for an AWS web service. The device needs to connect to AWS IoT, so we need to get the endpoint of AWS IoT. Import the client credential key file. The next, you will need to tell your device about the certificate you just created for it. Generate a header file to include your device certificate and signer CA certificate in your demo project. This step creates an AWS client credential key file that is used by FreeRTOS to save the generated certificate into ATECC608A. Step 31. Update AWS client credential file. Now enter the AWS IoT endpoint and the theme name into AWS client credential. Define used by FreeRTOS to indicate which endpoint it will connect to, which theme it will associate with. Step 32. Build again. Now, build the pre-ATOA project again with the new ATECC client credential and ATECC client credential key file. Step 33. Bound to MCU. Flash the new firmware we have just built to the MCU and reset the MCU to put up the new firmware. Step 34. Now we can connect to ATECC IoT server and publish and subscribe to control the LEDs. The device has successfully connected to ATECC IoT server using the key pair from ATECC608A now. In the demo, it will subscribe to a MQTT topic. It will control the LED according to the command it receives via this MQTT topic. We use an Android phone to send command to this MQTT topic. Let's try it. Press button on Android phone to turn the LED on. The LED are on now. Press button on Android phone again to turn the LED off. The LED are off now. Try again.